Good morning and welcome to this session today of Physical Science 1. Today and this coming Thursday are the last basically part of the chemistry model basically for this class. I'm hoping to have the review ready for you guys by Friday. I think for the most part is ready, but I just want to do some finishing touches on it. The review will be open until Monday evening, okay? The exam will start in the morning of Tuesday, which is, let me check the calendar again. I don't want to give you the wrong day. It's going to be Tuesday the 11th, a week from today. And then like the previous basically exam, it will extend to the evening so that you guys, if you're working in the morning, you're going to if you're working during daytime, you can take it in the evening and vice versa. The thing with it is also is that you will have the same rules as before, basically. There will be no makeups for the review. The review is graded and is graded for participation. Regardless of what you score in the review, that is going to be actually you're going to get the full credit for it as long as you take it, even if it's one attempt. That is to encourage you to go through the materials basically and prepare yourself for the exam. And the exam, as I said before, I mean, it's going to be on this chapters, the series of chapters, namely the ones that are dealing with chemistry. And I believe from chapter, I'm not sure, I don't remember the exact numbers. Let me open the, I know it's extended to chapter 19, but I don't want to give you the wrong, yeah, chapter 14 included, 14, 15, 16, 17, 18, and 19, okay? So those are the chapters covered in this exam. And then after that, on Thursday, we will meet again in regular time and so on and so forth. So there will be no class, not this, I mean, this Thursday we have a class, we have a regular class. But a week from today, on May 11th, there will be no live class because you're assumed to be taking your exam at that time. If you are during the morning, if you are taking the class during the regular times. So that's basically in a nutshell. Obviously, I will send more messages, more details into what's going on. So watch your message, your inbox from Canvas, where you get a lot of information about these things. Okay. So let's dive into chapter 18, and chapter 18 is quite a long chapter. So let me share with you the screen. Okay. So let me move this up close in here and minimize this window a little. Okay. So so we're going to be talking about the two main classes of basically chemical reactions, the oxidation and reduction, and what is a base and what is an acid, and how we measure that. That is really the entire chapter on this thing, on the content for this entire chapter. So basic concept is acids donate protons and bases accept them. Okay, so that is really the basic concept that you need to take from this one in here. Bases, though, and acids, they can have different strength in terms of how much they can give or take those protons, okay? And what is an acidic solution and basic solution and neutral solution depends basically on the concentration of hydronium in it, or so basically that is the basic concept in here. Let me get something in here. Oh man. Try to get some activity actually, but I don't know, okay? The thing with it is, I was hoping that you guys build your own battery, the chemical battery that is, but we will see, okay? And it's not hard to do basically with a lemon. Okay, all you need is just two different metals. Basically, we're going to talk about this one, two different kinds of metals with different affinities for electrons. and then a wire. And if you have if you have one of these diodes, you're in good shape. One, because this can run with very small voltage, typical of what you get out of a battery, out of a lemon, because lemon turned out to be a weak acid. Okay, and you're going to get light out of it. You should be able to light to have light running through it. Anyway, we will see. I don't know if you guys want to do that. It's fun. If not, especially in terms of the diodes, some of you probably don't have access to them. I have 3 types of diodes in here. Different colors, and they run with the same principle. Okay, so that is what you will need, because a light bulb that is more than that will probably require more voltage across it to see the light. Basically, you need more current running through it to see the light. This is a small battery that I use with a battery holder, with small light bulb that I have a light bulb holder for it too, and all of that. That's part of a kit that I got from Amazon. Anyway, we'll see. Okay. So again, we're going to talk about acidic rain and what it does basically in terms of the soil and plants and other basically structures that are metallic in nature, or even they have calcium in them. So because acids react with those, and losing and gaining electrons, those are the the basic process for ionization, and that is how you use that is what I was talking about, the chemical battery, the one that I was trying to describe earlier. Harnessing the energy of flowing electrons, that is basically what the batteries is. This is any typical battery, like this one is a photovoltaic cell. No, not a photo. This is a regular chemical battery in here. It uses the same principle in here that I was describing earlier, except that it has usually the carbon running all the way through, and then you have metals in the side, and you have a paste in there that is actually basic solution in there, and that is going to take the electrons from one side, makes the ionization from one side and another ionization from the other side, and because of the different affinity for charges, then you will have that one sitting. On one side, it's connected to the negative side, which is going to be the anode, and then the other side is your cathode. Okay, so that is basically the principle behind it. We use electrolysis, which is basically a way of cleaning materials and doing the same process that I was describing for building batteries. Corrosion and combustion are actually reactions basically over a long time of oxidation in this case that is typical and happens with metals everywhere. So again, these are the basic topics. These are examples of everyday acids that you can see, okay? Again, they donate protons, and proton is nothing but a hydrogen atom stripped out of its own electron, okay? So that's basically what the process is. So it's an ionized version of hydrogen atom. Bases, on the other hand, these are some of the typical stuff that you will see on a regular basis. These are bases. And soaps, for example, is a typical one. And again, this is where they accept the protons. So again, this is just a definition in here. So what is a proton? Proton is nothing but an ionized version of hydrogen atom. So this is your hydrogen atom, typical hydrogen atom. Hydrogen atom, when you have, of course, positive charge for the proton and negative charge for the electron. And when you remove the electron, you're left with the positive ion inside, which is a positive proton floating around, okay? So that is how we represent it. So it's the same thing in here in this representation. Again, this is just one way of remembering this, BAAD, okay? Bad. So base accepts, acid donates, okay? So again, which one acts as a base, which one acts as an acid? For example, in this case, HCl the hydrochloric acid in this case will donate its proton, therefore it's going to act as an acid. Water in this case will behave like a base, because it's going to accept that. And you will form out of it the hydronium ion and chlorine ion. So in this case, that is how it's going to happen in here. So in this case, water is behaving like a base because it took that extra proton, the proton that the hydrochloric acid gave it. Now, on the other side in here, so that's the point I was saying in here, because it's accepted to behave like a base. So this is the argument in here. Now, with ammonia, it's a different process. For ammonia, in this case, it's the hydrogen that gives its own, the water that gives its own hydrogen ion. So in this case, it gives a proton. So water behaves like the base. It's the other way around. Like the oxygen, like the acid, behaved like a base in presence of an acid, and vice versa in presence of a base in this case. So now, so the water H2O is the one that is the donor, and the ammonia is the one that is and the acceptor at this point. Okay. So, and you can think of the operation backward as actually the reverse. Okay. Okay. So, what happened to your classmates, guys? Not too many of them are attending anymore. Hopefully, it's going to show in the exam next time around. Okay, let me, with a quick survey in here, how do you feel, guys, about that project that I mentioned on building your own battery? Is it feasible? You have access to different metals. Iron, you should have it. The iron is any kind of paper clip is an iron. Okay, you can stick it into the lemon. And copper, copper is most of the conductors. Basically, you have it also in abundance usually in your household. So that should be accessible. The only thing is, how can you test the current in here? If I run it through a multimeter like the one I have it, I will see the current in here. Do you think that it's feasible for you guys? Can you do that or not? You have access to a light bulb like this one? Okay, that's fair. Anybody else? No? Okay. Here is the deal. Then, since I have you here, and this is going to be graded, okay, so that you know. If you have access to it, build it and share it in the discussion. If you don't have access to it, describe the principle. How is that for a task? Is this fair enough? Okay, very good. So this is going to be graded, okay, for participation. And if you can build it, that's great. Take a picture, well, the light is on. If it fails, that's fine too. Explain why do you think it failed? Probably because batteries, they run out of juice, and the way they run out of juice is the process of corrosion. So basically at that point, you run out of ions to ionize anymore, and at that point, they cannot do their trick, okay? So you may be in that thing. If you can't access to everything, so try to do, if you can, then basically describe how the process works, okay? So let's resume this thing in here, because I want to make sure that those who are not in here are not relying on some sort of just an exam thing in here, because that's not really learning if you're going to memorize the exam stuff and then come in the exam and, okay. So again, so all of these things are just to check the same points that I was raising earlier for different materials. Salt is actually the product of a reaction between a base and an acid. That's a typical one. This is NaCl, which is sodium chloride. That is a typical salt. So what happened when you have different kinds of basically acids mixed with different kinds of bases, then in this case, you will have different kinds of salts. Always the product is water. So there is always water, which is a combination of the hydrogen and the OH in here to give you the water in this case, H2O. So whether you're looking at hydrogen cyanide with sodium hydroxide, nitric acid with potassium hydroxide, and whatever you're going to look at in here, you're going to combine the hydroxide part of it with the hydrogen with a proton in here to form water, and then the other two, whatever it is, you're going to get into the salt, okay? Calcium chloride in this case because of the fact that calcium has 2 valence electrons versus chlorine, which has only 1. So you have CaCl2 in here to make it happen. Same thing for these, for the other 2 in here, okay? It can also happen when you have organic bases, for example, with a regular acid too. So you still have a salt in this case, albeit it's an organic salt, with chlorine in here, in this case, ion. The next chapter is going to deal a little bit of the organic chemistry, and that closes the book on this section in here. So strong acids and bases ionize in water completely, okay? So all of them, they will dissolve in here. In this case, you will have the hydronium ion formed. And that is really how you measure the strength of the acid, is looking at the concentration of this one. How much did you end up with this one? In other words, how many protons were captured in here, okay? Weak acids do not completely dissolve. In other words, you will have less concentration of hydronium ion. So that is basically, you will have more than a regular water does, but at the end, you will have very little at the end, okay? Compared to a strong acid. So again, this is the process I was describing earlier. This is what you're supposed to be doing. Obviously, this one is a very strong acid. Okay? Do not do this one, even if you have access to acid. This can be damaging, okay? You really have to have all kinds of safety. So what I'm asking you to do is use a lemon, which is a safe thing. I mean, that is the one that I want you guys to do. Do not experiment with this kind of a strong acid in this case, okay? Do not open your battery for the car that has a lot of strong acid in there, okay? Could be damaging. In normal water, water molecule, again, can act as both. One of them gives a proton, the other one takes a proton. And this is a hydronium atom. This is the representation in here of how much acidic the solution is. And this is basically how much basic the solution is. But because now each pair come in pairs and they form in pairs, they should be balanced. So in normal water, there should be balance. There should be enough of them to basically they will come in pairs. So these numbers, they will be exactly identical. And that's why it's a neutral water in this case. It does not have any, does not favor one or the other. In pure water, for every 1 hydronium ion, there is exactly 1 hydroxide ion. There is exactly 1 of them. As a matter of fact, this concentration is very small, and it's of the order of 10 to the negative 7 basically per parts per million. So it's a very small concentration. Not all of the water goes through this process, okay? Now, if you take that, then in this case, what I say in this case, both the concentration of the hydrogen, hydronium, and also the hydroxide ion, both of them are the same. Okay, it's balanced, so we say it's neutral. So the pH now is a measure of the concentration of the hydronium ion. If there is more of it, then it tips towards the acid. If there is less of it, then it tips toward the base, okay? Acidic solutions, they have numbers between 0 and 7. Basic solutions are between 7 and 14 when it comes to the pH scale. Now, when I say it's more of it, that means it's not 10 to the negative 7. It could be 10 to the negative 3. Remember, when the number is smaller, but it's negative, it's bigger actually, okay? The closer the number is to 0 on the negative scale, the bigger it is in terms of the powers, okay? Whereas on the other side, the closer the number to 0, the smaller it is. So that is why you might be a little bit hesitant to see, since the concentration has increased for the hydronium oxide, for the hydronium in this case ion. Why do I see that it's an acidic? Yeah, because it increased. It's closer to 10 to the negative, 10 to the power 0, and 10 to the power 0 is exactly this number, 0, and 10 to the power 14, in which case 10 to the negative power 14, in which case you basically have nothing of this. All of it is this one, okay? So this is exactly what I was talking about. Acidic solution has a pH that is between 0 and 7. Basic solution is the pH for its measurements is between 7 and 14. Okay. And for that, you use what is known in math as the log. So pH is a measure of the concentration of the hydronium ions, but it's not direct measurements of it. It's a measurements of the log in the base of 10. I know probably you have never, I mean, you have not used it probably before, but this is the number that is used. So there is a negative sign in front of it. So when you take the log of 10 to the negative 7, the answer is negative 7. It's basically what is in the exponent in here, what is sitting on top of the 10, okay? Since negative 7 is sitting in the numerator and in the top of the 10, basically above it as the exponent, you drop it. That's it. You drop that power. Since it's a negative times negative, so it's 7. So for pure water, pH is 7. Okay. So the pH now is, again, as I was saying, is just the power to which you raise the power to 10 to the power. Okay. So, for example, the pH of the log of 10 to the power 2, which is 100, by the way, is 2. Because 100 can be written as 10 to the power 2, which is 10 times 10, okay? 10 to the power 1 times 10 to the power 1, which is 10 to the power 1 plus 1, which is 10 to the power 2. So all you have to do is just drop that number, and you should be fine. So that is the log in the base of 10 of 10 to the power 2, because the base matters really. And you probably, a word of caution in here, when you have a calculator, if you're going to do this one, there are 2 main bases used in calculators. Then is the base 10, and this has the symbol log. There is actually the natural base, and the natural base is the symbol for it is ln. So if you're punching things on the calculator, you have to be careful, okay? This is the base E, okay? So that if you're trying to worry what is, and E is just a number, okay? E is just 2.71 something, okay? It's an irrational number, just like pi, okay? But it's another number that is a natural number occurring from some math stuff in here that has to do with the exponentiations and things like that. So this is, you have to be careful with it. It's not this one, it's this one in the base of 10. These are not the only 2 bases though. Any number can be a base, okay? That's why usually the log has an index underneath of it. So you'll probably hear me say in the base of 10, in the base of 10. When it comes to seismic activity down the road, also when we do geology, we're going to, again, use the same symbol, log on the base of 10, for measuring the strength of the earthquakes. And we use actually the Richter scale in that case also, which uses logarithmic scale. Logarithmic scale is a really very, very convenient way of representing numbers. So imagine yourself trying to describe this concentration without the without logarithmic scale. You're going to have trouble with it, because you start from a concentration, for example, of 10 to the power 0, which is all of it basically hydronium in this, all hydronium ions. There is basically no hydroxide ions. So in this case, it's 1. 10 to the power 0 is 1. And then you're going to 2, 3, 4, 5, 6, all the way to 10. Here you reach 10. By this time in here, you have this many digits just to go from 1 to 10. And this is just 10 to the power, I'm sorry, this is 10 to the negative. So it's all of it 0 point, okay? 0 point, 0 point. All of these things are 0 point now. So this is 0.1, which is 10 to the negative 1, okay? So we're going to this scale now. Actually, we're going decreasing now in concentration of hydronium oxide in this case, meaning that we have less and less of it now. So instead of 10 to the power 0, which is 100%, down to, at this point, 0.01, okay? 0.1. But that's not the entire picture. So I'm going to go from 0.01, and then starts to increase all the way to, I'm sorry, 0.01, and go all the way to down to my scale of 10 to the negative. Did I do it right in here? So probably I have to do my divisions correctly. Okay, this is not correct. Okay, I have to start with 0.000000000 all the way to 13 digits plus 1, 13 zeros plus 1, and then start all the way to this number, and then do the same thing in here, 0.0000000, 13 digits, 13 zeros plus 1, until I get to 10 to the negative 2. And so on and so forth, okay? So the concentration now is increasing ever since, or decreasing ever since this way, from 1, by this increments, until I get at the end, very small concentration at the end of the day, I'm going to get 0.00. It's going to be a very long process. My point in here, you cannot even write this thing. So instead of doing that, we use the log. So the log is much easier now to work with it. So if I say log in the base of 10 of 0, so the next one is 1, and 1 is actually this number, and 2, which is this number, and 3, and so on and so forth, all the way to 14. It's much easier to write 0, 1, 2, 3, 4, 5. So it's easier that way, because the concentration can be changing very little. I mean, a lot actually, as a matter of fact, but the difference in acidity and from one step to the next is not going to be seen that much. That is why we use this logarithmic scale. So it has an advantage. Okay, it has a lot of advantage to describing this big changes over a small range. So that is really exactly how you're going to. So big changes. Remember, the changes are from here all the way to probably several lines or probably the entire page, and maybe you're not done with it. So big changes over. You can represent big changes. I mean, you cannot change them, you cannot affect them, but represent big changes with small numbers, with few numbers. That is the biggest plus, actually, of the logarithmic scale. So I know probably you guys are not too familiar with it, but that's the point of it here. Okay. So again, in the base of 10, the log of 1,000. 1,000 can be written as 10 to the power 3. All you have to do is just drop this 3, and it's going to be there. Log in the base of 10 of 100 is going to be log of 10 to the power 2, and all you have to do is just drop this number. So if I ask you, what is the log of, let's say, for example, 231, you should know that it's more than 2 and less than 3. That's all. If you have a calculator, you can punch the numbers, and you are going to find it a number that is more than 2 for sure, and less than 3 for sure. As a matter of fact, probably it's going to be closer to 2, because 231 is closer to 100 than it is to 1,000. And I happen to have a calculator in here, so let me check that. Log of 231. It's 2.36. So that's what the number is. The point being in here is, it doesn't matter the exact number, but it's more than 2 and less than 3. And that is the point in here. So what is log of 59? Well, 10 to the power 1 is 10, and 10 to the power 2 is 100, and the number 59 is between 10 and 100, so its log is between 1 and 2. And that is really what you need to remember from these things, okay? If you can. If not, if you have access to a calculator that does the log in the base of 10, you can always do that. So that's exactly the discussion I was talking about in here. Now, when the power is negative, it's really going to still be this number. So the log of this number is 1000, is still 3. This one is 2. This one is 1. This one should be -1. 10 to the -2, which is 0.01, should be -2. You have to remember that this number is not negative. This is still positive, and its log is negative. 10 to the -3, which is 0.001, is actually -3. And in here sits between -1 and 1 is the number 0. So 10 to the power 0. So a log in the base of 10 of 1 is 0. As a matter of fact, the log of 1 in any base is always 0. Okay. So this is the discussion that I was talking about in here. So there are 2 zeros, and the log is just a count for how many zeros on this side and how many negative zeros on the other side. And here there are no zeros. So the log of 1 is 0. So what is the log of 1? It's this power, 0. Okay. Look at it, log of -7. It should be -7. But don't forget the definition has a negative in it to begin with. So the negative times negative what is the definition that we started with? Has a negative in it too. That's why the log can never be negative. It's always positive because of the fact that the maximum you can have of hydronium oxide is 100%. And that's why the log of 1 is going to be 0, and you cannot have any number for the pH less than 0. pH cannot be less than 0. It has to always be greater than 0. As a matter of fact, the maximum it can be is 14. So it's anywhere between 0 and 14. If you have an acid of concentration 0, that is going to be deadly. If you have an acid that base that is 14, that is going to be also as equally dangerous. Okay, both of them are so damaging. So enough about the log. Okay, assume that you know how to do it, and that's basically in a nutshell how you find it. Okay, so if you're math-minded, that's fine. If you're not, that's fine, because that's basically how you look at it. So what you need to remember is on this scale, on this side, between 7 and 14, it's flipped, okay? So what you were looking for before was upside down. Now it's from this numbers in here, okay? All the way to 10 to the power 14, okay? So an acid rain has a pH lower than 5. Okay, so it's acidic because of the usually the what we lose in the atmosphere in here. It's the pollution really that causes the acidity, and it's so this SO2 is from the releasing of coal and oil, and so it becomes acidic, and this is some of its damages that it can do. Okay. Even the rain in here, the forest in here is damaged by the rain. And in here also, again, because it interacts with the calcium in the rock. So it's going to damage the rock. And it can be devastating, not just to, and it's again from this carbon dioxide that is emitted and forms this, okay? So again, acid-base reactions, it's a transfer of protons. Acid-base reactions, transfer of proton, oxidation and reduction. So that's a name for the this reaction. I see that there is something in the chat in here. Which question that is? I lost it, Corinne.
I was asking about the log and the math equations.
No. Okay. At this point, we're not required to be really that much deep into mathematics, honestly. But just to give you an intuition, at least an understanding of what that might be, okay? Okay. So So transfer of electrons. So the oxidation is the loss of the electron. So this is basically how you look at it. So in this case, the sodium gets oxidized and by losing 2 electrons. And whichever accepts those 2 electrons is going to be, in this case, reduced, okay? Sometimes you will see it as a redox operation or a reaction. It's referred to sometimes as redox. If you see this word, you know exactly what that means, reduction and oxidation. And I'm not too fan of this thing in here, in terms of how you can remember it. Anyway, so this have the tendency to gain electrons, which means they can be reduced. This, they have the tendency to actually lose electrons, and they can be oxidized. This interact very little at all, if any. So this is in a nutshell what this oxidation and reduction is, okay? Loses electrons, gains electrons, or gains an oxygen, which is the same thing, loses oxygen or loses hydrogen and gains hydrogen. Okay, so again, I mentioned this one as this is part of the things that we're going to be doing, hopefully. And if you can do, at least you document how the process works for the electric currents. And so batteries and fuel cells. And so you have to have 2 different metals. In this case, copper. Oh yeah, it's used also in coins, okay? And iron, okay? As long as you can stick the copper inside the acid so that it can work, you should be able to. Do not try it with a big light bulb. I mean, if you get it to work with a light bulb, that means you have a very strong acidic solution, okay? So do not try it, okay, with that, okay? Now, if you don't have access to a lemon also, what is that, the other one? One that is used in salads. I lost the name right now. My brain is not keeping up right now. I'm still not. Vinegar. That's the other word I was looking for. Okay. Vinegar should do. Okay. If you don't have access to a lemon, vinegar should do. Albeit both of them are weak acids, though, so they are not really good. So that's why you will need something sensitive. Now, if you can get it to work with a bigger light bulb, like I said, that's great, but I don't know how you're going to do it, okay? Please do not put a battery in between to help it in the process, because that's really not good. The whole point is to create a battery in this process, okay? Fuel cells also use the same principle in here. And I was describing in here that you have the graphite rod, which is the cathode in this case. And you have the membrane in here, which is protective in here. And you have the zinc cup, which acts as the anode. And that is where you're getting the negative side in here and the positive side on the cathode. And that will run it. If you run it through even this light bulb, you're going to see electricity on it through. But that has a big, basically, output of electrons. Okay. So the positive electrode is the cathode, where the reduction occurs, and vice versa in the anode. Okay, that's where the oxidation occurs. So these are different kind of batteries. Okay, rechargeables are made up of lithium and. Okay. Again, they convert chemical energy. This is the basic principle. So, and this is probably one of the questions you might see in the exam or in the review exams and things like that. So fuel cells convert the chemical energy of a fuel into an electrical energy. So that's what it does, okay? So the principle and the details behind it, basically, it has to do with the affinity for the protons or the electrons or basically the ions in this case in general, how they move, as long as you have an imbalance of charges one way or the other. You connect wire on the outside and the charges will move, okay? So this is the basic principle behind it. Electrolysis is used to basically deposit, to produce chemical change, okay? So basically to purify metals or recharge your car batteries. So the same principle in here for it. And the purification just by removing the material that needs to be removed from there with the deposition, or to protect it also you deposit using the same principle, as long as you have charges in here, and the ions will move on one way until they deposit on the other. Now, corrosion and combustion. Corrosion itself is basically, in this case, you have an oxidation operation of the metal. Okay, and this is what you see when you are near, especially iron. In this case, the color changes. The copper changes to a greenish color. Okay, corrosion, the process whereby a metal deteriorates through oxidation reduction reactions, and that's why the battery runs out of juice at the end of the day, because you're doing that on a regular basis until you run out of metal to basically do this operations to, and at the end you don't have a good battery, so you have to go and replace it. Okay, corrosion, the process whereby metal deteriorates through oxidation. It can be prevented by doing a coating. So if you coat it, for example, with zinc, in this case, what happened is the zinc oxidizes first and protects the inside. So that's exactly what you do, for example, for boats, because you're making them out of iron, and iron is highly oxidizable. So if you're going to put it in the ocean, it's going to be useless after a few usage. So what you do in this case, you protect the layer, the outside layer that oxidizes first and becomes protective for the inside and does not oxidize anymore. So there is a thin layer that forms, and that's it. Combustion is an oxidation reduction operation between a non-metallic material such as wood and oxygen. Okay, so you need some sort of an organic material in here for this operation. Okay, so this is in a nutshell the entire chapter. Okay, I know I did not go through all of the examples, and I'm hoping that you guys go through them. And if you have any questions, please send them over. And as I said, we still have to meet this Thursday before the exam. I mean, the stuff that is needed for the exam. And please take care of that assignment. And I'm going to change this one to a graded assignment so that you guys are fully compensated for doing the work for it. Good shape? Good. Very good. So I'm going to stop the recording now.